AP Calculus, section 4.1, page 4. Okay, continuing some examples here. Let's analytically find the absolute extrema of f of x equals e to the negative x squared. Then verify your answer graphically. So analytically, we're going to start by looking for critical numbers, which means we need to find the derivative. And f prime of e to the negative x squared, that is e to the negative x squared times the derivative of the negative x squared, which is a negative 2x. So we have negative 2x e to the negative x squared. Let's go ahead and rewrite this e to the negative x squared to get rid of that negative exponent piece. And we're looking at negative 2x over e to the x squared. There's the derivative. Now looking for those critical numbers, we need to look where f prime is equal to 0, where f prime is undefined, and f prime does not exist. Alright, f prime equal to 0. Since we have a fraction, the only way a fraction can equal 0 is if the numerator is equal to 0. And the only way this numerator can equal 0 is if x is equal to 0. F prime undefined, that's looking for, let's jot this down, numerator equals 0. F prime undefined, that's denominator equals 0. Alright, so we want to know where the denominator e to the x squared could ever equal 0. Well, e is a number, 2.718. 2.718 to any power, regardless what x is, that'll never equal 0. So there aren't any here. And an f prime does not exist is looking for slopes from the left not equal to slopes from the right. You're going to see this mostly in a piecewise defined function. Alright, so our only critical number then is x equals 0. And after we find our critical number, then we're going to go ahead and set up our t-chart with the critical number. And then we need to set up our endpoints. Oh, where's our endpoints on this one? There aren't any. Uh-oh. No, I'm kidding. I knew that. There aren't any endpoints here, so a couple of things are going on. One is that the extreme value theorem doesn't hold. That means that the initial conditions are not satisfied, which means it has to be on a closed interval. That function has to be continuous on a closed interval. The initial conditions aren't satisfied, so we say the extreme value theorem doesn't hold because f of x is not defined on a closed interval. That means that you can't guarantee that there is an extreme value, an extreme maximum, and an absolute max and an absolute min. There might be, but we can't guarantee it. The extreme value theorem says if we have a continuous function on a closed interval, then there must be an absolute max and an absolute min. Let's think about this though. Could we kind of pretend that the endpoints are some very large negative number and some very large positive number, and look at what's happening here for these endpoints and see what we can come up with. Let's just look and see. So we can evaluate this function at this critical number 0. So we need to evaluate the original function. The original function, this is going to be e to the negative 0 squared. So e to the 0 is 1. All right, now let's put in a very large negative number. Very large negative number. Think about this. This is 1 over e to the x squared. Large negative number in here, squared, turns large positive. Then we have 1 over e to a very large number. That's going to 0. Does it really end at 0? No, it goes to 0. It gets close. Likewise, if we put in a positive infinity here, e to a very large number, this is very large in the denominator, so the whole fraction goes to 0. All right, so from reading this, this is looking like we have an absolute maximum value absolute maximum value is 1, and it occurs at x equals 0. There is no absolute minimum because we don't actually ever get to 0. All right, now let's go ahead and take a look at this graph and see if that matches what we want to say. So let's graph y equals e to the negative x squared. Standard viewing window. Ooh, that's really hard to see here. Let me open that up a bit. Let me look again, see what I want to do. Oh, I could go like -5 to 5 and maybe -2 to 2 in the y's. And there we go. Yeah. All right. What's going on over here at this 2? I just want to see what's going on because I can't really tell. So I'm going to trace an arrow over here. And look at your y values. Look how small they're getting. Huge small. Do they ever turn negative? No, not negative. And over here, let's go to the other side. Same thing. Yeah, very, very close to 0, but never really right there. So if we graph this, we are absolutely seeing something like this. Getting very small here, but never quite hitting. And that verifies our information. Taking a look at this next one, let's find the absolute extrema of this function. F of x equals the natural log of 2x plus 1 for x between 0 and 3. Then we're going to verify our answers analytically. Now this one, it wasn't tricky. I did give you that closed interval, so that's nice to know on this one. Let's start looking for those critical numbers. So we'll find the derivative. And the derivative of this ln, it's going to be 1 over 2x plus 1 times the derivative of the inside, so times a 2, which is 2 over 2x plus 1. There's the derivative. Now we start looking for those critical numbers, so we'll set up f prime equal to 0, f prime undefined, and f prime of x does not exist. All right, f prime equal to 0. When we have a fraction, the only way a fraction can equal 0 is if the numerator equals 0. Can that numerator ever equal 0? Nope, none this time. How about f prime undefined? Undefined is denominator equal to 0. Could this denominator ever equal 0? Yes, it can at -1/2. Does not exist. You're going to see that in piecewise. This is not piecewise, so none here. Okay, here's our only critical number. So let's go set up our t-chart then. With a critical number of negative a half and the endpoints of 0 and 3. And let's start evaluating. Let's plug this negative a half right in here. And 2 times negative a half is negative 1 plus a 1, 0. So I need the natural log of 0. Oh, that doesn't exist. Yikes. Oh, but wait, look at this critical number, negative a half. Was that in the domain? Nope. So we didn't even have to check this one, and we probably shouldn't have checked it. It's not in the domain. So we didn't even really need to check it up here. I just kind of flew by just in case that happens to you too, so you can kind of go back and check. All right, look at this next one though, 0. Can we plug that in? Absolutely, we plug the 0 in and we're going to get the natural log of 1. And the natural log of 1 is 0. Over here for the 3, that gives us the natural log of 7, which I do not know what that is off the top of my head. Do you? That's 1.945. All right, so what are we seeing here? All we really have is that. So 0 is smaller, so that's a relative minimum. There is a relative minimum, and that relative minimum is 0 at x equals 0. The relative maximum is a y value, and that relative max is 1.945, and it occurs at x equals 3. Okay? Last bit, confirm your answer graphically. So let's go ahead and graph this. Natural log of 2x plus 1. Standard viewing. And here we go. All we're really interested in is 0 to 3, so maybe we can shrink this a little bit. And let's go negative 1 to 4. And y's, let's go negative 2 to 5. Here we go. Sure. If we sketch that graph to verify, and that should make sense to you that that's the shape of a natural log graph. And what do we have on here? For this interval between 0 and 3, 0, 3, we had a maximum, a relative max, right here at 3, 1.945, and a minimum right over here at 0, 0. Okay, thanks for tuning in.